So let us now understand the next functionality of data link layer, which is error detection and correction. So this topic is easy and interesting at the same time. There has been many gate PYQs that they've asked from this topic. So let's see this topic, this very nice topic. So the second functionality, apart from framing, okay, framing is done. Okay, now the second functionality that we are looking for is error detection, right, and correction. So let's just see what does this mean. So basically, we want to detect the error if there is any error in the data transmission, which means suppose we are sending the data and if some bit get flipped, okay, then we want to detect that, okay, if there is some error or not, right? So we sometimes we can only detect, sometimes we can correct also, which means we are not only detecting that there is error, we can even correct, which means like we know that, okay, in which bit the error is, okay, so we can even do that. Like I will tell you that how, but sometimes we can even correct the error. So that's why error detection is there, error correction is there. Now in the error detection there are like 2-3 methods. In the error correction also there is just one method which is in syllabus, Hamming codes, right? Now the way that we will study is basically this, okay, this pair, which means first we will study parity bits, okay, and how to detect the error. Then we will go to the Hamming code, and then I will tell you that how to correct the error using the Hamming codes, right? So basically this is the order in which we will study, right? We will study this pair, and then we will study CRC, and then we will study checksum. Right, so let's just start with the first thing, which is parity bits, okay, but before that let's just see that how we can detect the error. Okay, let's just see that what is that very naive approach that we can do to detect the error. So this is the attempt one, which we are calling repetition. Repetition means the same thing I'm repeating multiple times. For example, if I'm sending this data, then instead of sending this data, I am sending this 3 times. I mean 1 2 3, and whatever we send, it is called code word, okay. I mean you can call the original thing as data, okay, or packet or whatever, right? Okay, you can call the original thing as data, and then you can call this thing as code word, okay. So whatever I'm sending, then I'm repeating it, right? Now suppose some bit get flipped. For example, this instead of 1 1, okay, instead of 3 times 1, it is coming like 1 0. Then we get to know that, okay, since these three are not equal, it must mean there has been error. It is possible the error could be like, I mean the original could be like 1 0 1 0 1 0, and the error could be in these 2 bits, right? I mean the error could be anywhere, like that's okay, but the error is there, okay. If these three are not equal, then I know that error is there, okay. That's what my concern is. So basically if I'm repeating the data, then I can detect the error, okay. I mean not all the errors, I mean it is possible that this 1 1 get converted to 1 0 1 0 1 0. I mean I'm sending the 1 1 1 1, but ultimately it is getting converted to 1 0 1 0 1 0, and I think that, okay, this is, since it is matching, then there is no error. So sometimes we are not able to even detect the error using this method, okay, the method that I'm proposing, which is repetition, right? So if you're repeating, then mostly you might be able to detect the error, but sometimes you might not be able to detect the error, right? See what I mean to say, that if you are sending, I mean the original is 1 0, but you are appending 1 0 1 0, right? If you are sending this, and then ultimately you get, let's suppose 1 0 1 0 but 1 1, okay, then yes, you can detect the error, right? This case is basically you can detect the error. But suppose you are sending 1 0 1 0 1 0, but ultimately you receive as 1 1 1 1 1 1. Okay, suppose you receive something like this, then you will think it is correct, right? I mean you will think that it is correct, so you will not be able to detect the error, and you will accept it thinking it is correct, will not be able to detect this error in this method. I mean there could be some other method we will see apart from the repetition, where we can detect some errors always, okay, but here in this case you will not be able to detect this error, right? And thinking it is correct, and you will accept it. I mean receiver will accept it. This is receiver, right? This is sender is sending this, but suppose receiver get this, it will think it is correct, isn't it? So basically we can repeat the data, but obviously there is a problem with the repeating the data. The problem is that pros are that, okay, this is very simple, right? And the cons are that how many times we need to send the message, okay. I mean it's not like that we can only send 3 times, then we are we are doing very good. So if we are repeating 3 times, then where this 3 number is coming, I mean how to decide this magical number, like we are repeating 3 times or 2 times or 5 times, like that, right? So how many times you need to send the message, and don't know when the message actually received is the correct message. Like we don't know, right? It's a correct or wrong. So for example, in this case, we don't know it's a correct or wrong, right? I mean, it is a wrong message, but receiver might think it is a correct message, okay? Because receiver might think that he might have sent 11111, and I might have received 11111, right? So there is no error, and this also will be accepted, right? This also will be accepted, and this also will be accepted, thinking there is no error. So anyway, this was the very first naive method, which is the repetition method. Obviously, it's not very good method, right? So apart from repetition, what we do, we basically go to the some other things which is called check bits, okay? So repetition is one of the way, but obviously it's not popular, it's not even mentioned in most of the places. But in one of the book, which is Frozen, I think I've taken this screenshot from the Frozen. I think they have mentioned repetition as a method, okay? Anyway, so now let's just come to the main idea. The idea is that instead of repeating the data multiple times here, okay, I'm calculating some function, okay? So which means, let's suppose I'm sending the data 11101, okay? Let's suppose I want to send this. So before I send this, what will I do? I will add some bits to it, okay? Which means this is 1101. I will add some bits to it. So what are the bits? So could be anything. For example, some function. Maybe the function is saying that JOR everything. Okay, if you JOR everything, this is basically 1 and 1 0 and 0 and 1 1, right? Then 1 will come, right? Then this is basically JOR of. I mean, this is a function of your data, which is JOR of your data, right? Data bits. Something like this. I mean, you are calculating some check bit. We are calling it check bits. It could be multiple bits. Let's suppose second bit, second number could be, let's suppose 0, which is coming out. Let's suppose you are doing AND operation of all of this. Okay, if you do AND all of this, then you will be getting something like this. I mean, basically, what we are doing, instead of sending data directly, or instead of repeating it multiple times like a naive way, what we are doing, we are basically saying, let's just add some function of the data, okay? So basically we are adding some function of the data. This is the main idea in this error detection, error correction, whatever you say, okay? So we add some bits, we are calling it check bits, and at the receiver side, what happens, it's a transmission medium, you send it to the network, then once it receives, okay, I mean, this is basically common. I mean, I hope you're getting what I'm, this diagram, basically the diagram, you can understand diagram like this. This medium is common, right? Okay, so once it receives the data, then it may be possible that that whatever you're getting, so basically what it will do, it may be possible that there is some flips in the data, right? I mean, instead of R, it could be R dash, instead of D, it could be D dash or something, okay? Then we again do what the function is known, right? I mean, the function is just like a mathematical function is also known to the receiver. Then receiver will again apply this function to this data, and it will check whatever receiver is getting should be same as this. For example, if I'm sending 1101, and then I'm adding a JOR of this. JOR of these all bits is basically 1. Now once you get it, okay, suppose you are getting 1101, and then you get 0. Receiver will do what? Receiver will apply the function on this. Receiver is getting 1, but here it is 0, so receiver will get to know, okay, there is an error. Okay, obviously we need to understand this in very good detail, but the core fundamental is this, that we are going to add some bits, and then based on that we are going to take a call. Okay, that's the only thing I want to convey currently. Okay, don't worry about much of the things. So the only thing that I want to convey currently is basically something like this, that we add some bits, instead of repeating, okay, some bits to data, and using those bits we take a call whether there is an error or not. Okay, using those bits, receiver take a call if error is there or not, if error occurred, right, or not. So that's how receiver will take a call. Don't worry, this is just an idea. You will obviously get to understand this in very good detail. So let's see first method, which is parity method. Okay, so what we do here, we add, as I told you, we add some bits. We are calling it parity bits or check bits, doesn't matter. So we add some bits here, okay? Just like, I mean, the general idea that I told you. Okay, here, I mean, in every method we will be adding some parity bits. So how to calculate those parity bits, something like this, that I will just tell you. Okay, so In this parity checking, what we do, we add just one extra bit to the data. Okay, just one extra bit to the data. Just one bit we add. And it depends on whether we are using even parity or we are using odd parity. If we are using even parity, okay, then total number of ones must be even, which means 1101. Okay, now even parity makes sure that whenever you are transmitting, okay, then total number of ones must be even. So currently 1 2 3 ones, then you can write one more one. Okay, so that's how you will send the data. So you can say the data is 1101, and the code word, we also call it code word. Okay, code word, I mean, after the appending, we call it code word. It is 1101, and then one more bit you append, which is basically 1. Why we are appending 1? Because to make the number of ones as even. Okay, this is just like even parity. Okay, very simple idea. How it help us, I will just let you know. Okay, but I hope that what we do is clear, right? We just add one bit depending on that the number of ones in the data originally. For example, if you have 1001, this is the data, right? Then originally number of ones are already even. Since number of ones are already even, that's why you will not add one. You will say that, okay, let me add 0 here, which means total number of ones should be even. Okay, so that's how you will add. In this data you will add 0. So basically here the data is 1001, and the code word, what is the code word? You will add 0 only, which means 1001 and 0. You will add 0 only. Okay, I hope you understood. ठीक है. So this is basically the data, and this is the code word. The whole thing is called code word, right? It depends on whether we are using even parity or odd parity. For example, let's just first go even parity, and then I will talk about the odd parity. For example, this is the data. What will the code word? What will the transmitted code word? In even parity, number of ones should be even. So first of all, let me just write the data, okay, as it is, and then what is the code word that we will be using? So basically 4 ones are already there, so you will append 0, right? You will append 0. 4 ones are already there, 1 2 3 4, right? You will append 0. That's all. Even parity is done, right? Now if it is odd parity, then number of ones should be odd here. So if you take the same data, now number of ones should be odd. Currently it is even, so you will add 1. Okay, but the odd parity you will add 1. That's all. Very, very simple. How it help us? I will let you know how it help us to detect the error. But currently I hope the even parity, odd parity things are clear, that what we do. Okay, why we do, I will just tell you. Okay, so for the even parity, the total number of ones in the data and the parity bits together should be even. Okay, so it is basically the important part is that data and parity bits together should be even. Okay, and data and parity bits together should be odd. That's how the parity works, right? Now let's just see that how it is helping us. Okay, so what if there is an error, and how to help us in the error? So for example, again, this is the parity bit. You can add the parity bit here. In the question, they will define that, okay, the parity bit is at the start, at the end. Okay, generally at the start or at the end. Sometimes they can also say it could be between. I mean, in the question, they will exactly give the syntax. Okay, generally it's at the end. Okay, or at the start. Now let's just see how it is actually helping us. For example, let's just take something. For example, let me take 1011. Okay, let's just take this data. Let's just fix some parity for the sake of discussion. We will not keep on switching. Let's just take even parity, which means total number of ones should be even. Okay, now when you transmit this, then you have to obviously append 1, because total number of ones should be even. Okay, this is the data, this is the code word, right? The whole thing is code word. Now you're transmitting it, right? Now suppose some of the bits get flipped. Okay, you can flip something. Okay, suppose one bit, let me just flip one bit. Suppose one of the bit, suppose this, instead of 1 you get it 0. Okay, suppose you get 0 here, instead of 1 you get 0 here. Then will the receiver be able to detect? That's my question. This is the sender, this is receiver. Will receiver be able to detect this error? Let's just see. Receiver will find the even parity. Okay, receiver will use this, will find the even parity. If you use this, the even, based on the even parity, this should be 0. I mean, parity should be 0, right? But parity is 1. So receiver will be able to detect this error. if this bit or any of the bit get flipped, if there is one bit of the flip, okay, if the data bit get flipped, then obviously like receiver can detect the error. Okay, so receiver will be able to detect the error. Let me first write it, then I will tell you more things. Okay, receiver will be able to detect the error, right? Now suppose that instead of this is same, which means the data is same, but instead of the data bit, suppose the parity bit itself get flipped. For example, you are sending this is the same data, okay, but here let's suppose this is 1 1, you receive 1 1 only, but then the parity bit get flipped, okay, the parity bit get 0. Then what will happen? The receiver will able to detect the error. See, receiver will find the parity using this. The parity using this is coming out to 1, right? But here the parity is 0. So receiver will again be able to detect the error, right? So receiver can detect the error. Receiver can detect the error. See, I hope my point is clear to everyone. That the point is that you are having some code, and if one of the bit get flipped, then it could be parity bit, it could be data bit, then the whole equation, the number of ones should be even, and the whole number of ones should be even. That will be changing, the equation will be changing, right? The number of ones should be even, or the number of ones should be odd, like in case of odd parity, that statement will be false if one of the bit get flipped. Okay, so if one bit get flipped, then receiver will be able to detect the error. What if two bit get flipped? For example 1011 is there. Okay, what if two bit get flipped? See, currently you are adding one, right, to make the even parity, right? Now suppose more than one bit get flipped. For example, this get 1, this get 0, and then everything else is same, which means this is 1 and this is 1. So suppose more than one bit get flipped. So here you can clearly see these two are getting flipped, right? These two are getting flipped. Instead of 0 1, you have 1 0. These two are getting flipped, everything else is same. Now number of ones are again even, because more than 2, basically number of ones are basically not changing. If it is previously odd, then it will also odd. If it is previously even, then it is even only, right? So here receiver will not be able to detect the error. Okay, here receiver will think that okay, everything is fine, number of ones to the receiver, number of ones should be even. Okay, because we are working with even parity. See, the everything will be applying exactly same for the odd parity also. So it's not about the even or odd parity, there is any difference. I'm just taking even parity as an standard. I mean, in our lecture, as a standard case, you can have odd parity also, right? So here the receiver job is to check whether total number of ones are even. If the total numbers of ones are even, the receiver will not be able to detect the error. Here receiver will not be able to detect the error. That's the point. Okay, here receiver will not be able to detect the error. Earlier receiver was able to detect the error. If only one bit get flipped, then number of ones, if it is even, okay, let's just again let's just keep it even, number of ones will not be even now. But here again number of ones are even. Now let's just take the other case. Suppose 3 bits get flipped. Okay, suppose 3 bits get flipped. For example, this is 1100111010. Okay, let's suppose this is the data. Then how many bits are there? How many ones are there? 1 2 3 4 5. So you can add one more one as a code word, right? I mean, in the data you can add one more one. Now at the time of receiving, let's suppose 3 bits get flipped. Okay, so 1, and then let's suppose this get 0. I mean, this get flipped, let's suppose. Okay, this get 0, and then let's suppose 1 0, then all are 0, let's suppose. Okay, and you can flip anything. Okay, then these are ones, let's suppose this, or maybe let me just flip this. Okay, this get flipped to 0, let's suppose this get flipped to 1, and then 1 0 1. Okay, I mean, basically I'm flipping just 3 bits, right? So those 3 bits that I'm flipping is basically this one and these two. Okay, so this one got flipped and these two got flipped. Okay, so suppose 3 bits get flipped. In that case, what will happen? See, the number of ones, just count the number of ones. It should be even. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Yes. So it is odd actually, right? So this will be detected. Receiver will be able to detect this. Receiver will be able to detect this. So basically, in this scenario, if you are flipping odd number of, if you are flipping 1, 3, 5, these many bits, then receiver will be able to detect it. Okay, because the number of ones, whatever the you have decided, even or odd, okay, doesn't matter, because the number of ones will get changed. Okay, if you have decided, okay, let's keep it even only. Okay, if the earlier it should be even, okay, the moment you are sending it should be even, but if you are flipping 3 bits, then again it will be odd. If you are flipping 5 bits, then it will be odd. If you are flipping 7 bits, the number of ones will be odd. So basically, number of ones will be changing. Okay, from even, like, even is the standard one. Okay, even parity I'm using. So ultimately you will be getting odd number of ones here, which means this parity method, okay, or parity check method, whatever you like to say, parity method, this can help us detect 1, 3, 5, 7 these bits error. Okay, which means odd bit error. If number of errors are odd, then it can find. Okay, doesn't matter whether you're using even parity or odd parity, but if the number of errors are, basically total number of errors are odd, okay, then it can find. Okay, then it can detect. But if total number of flips are 0, basically 0 is a good case, so if there is no error, so let me take 2, 4, 6, like this. Okay, bits error, total number of flips are these many bits, then this method will not be able to detect, Okay, I hope you are understanding this. So basically, in this method, if it is one bit error, you can detect it. If it's 2-bit error, then you cannot detect it, because earlier even, now also even. So how you can detect it, right? So basically, receiver will think that this is the correct code word. Okay, although this is invalid one, but receiver will think that this is a correct code word. Understood? So that's the problem, because this is actually the this is a valid code word. You could have sent it, right? There is no harm in sending this. Okay, originally you could have sent it. Receiver will think that this is the original one and there is no error, right? But if it is 3 bits again, then the number of bits will be changing. Okay, if it is earlier even is something we have decided, so then it will be odd actually. Okay, so if earlier is odd, then it will be even. So anyway, like whatever you have decided, opposite of that will happen. Okay, if you are sending even, then ultimately it will be odd. If you are sending odd, then ultimately this will be even. Okay, like that. So opposite of thing, a receiver will receive. Then receiver will be able to detect the error. Receiver will think that, okay, we have agreed on even, now I'm getting odd number of ones, then it means there is an error. Okay, or vice versa, we have agreed on odd, but now we are getting even number of errors, even number of ones, then it means that there is some problem. Okay, like that receiver can detect the error. Let's solve this question. This is the nice question. Which of the following is or are true about single bit even parity? Okay, even parity you are using. Doesn't matter you are using even parity or parity, in terms of the analysis both are same. So receiver can detect all single bit errors. If this is single bit, which means 1 bit error, yes, receiver can detect. So this is the correct answer. But since it's MSQ, so let's see more options. Okay, single bit error means 1 bit error. Receiver can detect all burst errors. Burst error means like it could be 2 bit, 3 bit, 4 bit, 5 bit. Or any more than 1 bit. So obviously no, right? Not all. Okay, not all. In burst errors, only the errors which are either in 3 bits, 5 bits, 5 bit error, 3 bit error, 7 bit error, like that, right? Receiver can detect burst errors if corrupted bits are at odd positions. See, position doesn't matter here. Okay, the position doesn't matter. See, this is just to confuse you that, okay, the corrupted bit, I never talked about the position. We are anyway counting, okay, counting the number of ones. We are not talking about the position of one, right? We are anyway counting. So that's why this is And this is also wrong. Receiver can correct all single bit error. Single bit error says receiver also know the position of the corrector bit. See, it cannot correct. You will get to understand why when we see the correct how to correct the errors. So it cannot correct. It can only detect. So even though this is MSQ, still only A is the correct answer. Okay, it can only detect single bit error. It cannot correct. Okay, how to correct it? Once we see the correction methods, then you will get to understand that why it cannot correct. Okay. Yeah, so this was very small topic. It is just saying that if it is even bit parity you are using, then total number of ones should be even. If it is odd bit parity you are using, total number of ones should be odd. That's all. Okay. Now let's just see. As I told you, we are going in the sequence. So let's just see the Hamming codes. Okay. Now we will see this the Hamming codes and then Hamming distance and all. Okay. So let's see what is Hamming distance. So this method, by the way, this method will not be able to detect. This method will even be able to correct. Okay. This is interesting. Okay. You not only detect the errors that okay there is an error. You just not only get to know that okay there is an error. You can also correct it because you know the position that okay this bit got flipped. How to know this? We will see. Okay. We will see. So for that, let's just first see what is the Hamming distance. Let's now see the next topic, which is Hamming distance. So let's see what is Hamming distance. Suppose that they have given you two, you can say code words or two words, okay, and then they ask you Hamming distance. So basically, the Hamming distance is the number of bits differences in these two words, okay. So how many bits are different in these two? So you can say that okay, two bits are different. So Hamming distance is 2 here. Okay. What about this? 10101. Here the Hamming distance is see, 1 and 1 is matching. This bit is flipped and then this bit is matching and then this bit is flipped and this bit is flipped, right? So 3. So you can say that these 3 bits are not matching, right? These 3 bits are not matching. So that's why it is 3. So basically total number of differences or total number of bits which are different from one code to another, that's called Hamming distance. The distance between two words of same size is the number of differences between the corresponding bits. Okay. So find the distance between these two vectors. So basically you can find, you can say that, okay, this is not matching, this is matching, this is matching, this is matching, this is not matching, this is not matching, this is matching, this is not matching. I think 3, right? So 3 is the answer. That's very easy. Okay. So 3 is the answer here. Sorry, 4. I think I missed something. This is not matching. This is also not matching. Okay. This is also not matching. So that's why 4 is the answer. Okay. So distance is 4. Now there is a concept called minimum Hamming distance. Okay, so what is the minimum Hamming distance? So minimum Hamming distance is the smallest Hamming distance between the set of pair of codes. So for example here these two are the 2 is difference between these two. And can you get 1 also? I think this is 2. This could be also 2. Yeah, I think 2 is the answer here, right? So basically, I mean, in between this is 2. In between, I think this is again 2. In between these two. Yeah, again 2, right? Last 2. Okay, last 2. So basically, let's suppose that let's suppose this is 0 also, okay, or something like this. I mean, basically you need to find the minimum, okay, minimum of among all the pairs. So currently it is coming out to be 2, right? So currently it is coming out to be 2. So find out the minimum distance. So here it is 2. So basically the minimum Hamming distance, which means that you are given with all the pair of codes and among all the pair, what is the minimum Hamming distance? Okay. So find out the minimum Hamming distance here using the set of valid code words. So which means this is valid, which means this is valid, this is also valid. Okay, the valid code words are these. These are the invalid. Okay, these are the invalid. After one flip, you are getting invalid or something. So basically, what is a valid code word? What is an invalid code word? Valid code word is something which is valid with your rules. Okay, for example, let's suppose if I ask you the valid code word. Valid code word is basically in even parity. In even parity, you can say in even parity, all code words having total even number of ones are valid code words, right? Total even number of ones. Even number of ones are valid code word. Okay, so there are some set of valid code words. I mean, even number of ones you can generate. So there are some set of valid code words. Let's suppose these are the valid code words. Okay, for any error detection, error correction, there are some set of valid code words. These set of valid code words are known to sender and receiver both. I mean, they can calculate, or this is known. I mean, I hope that's fine what I'm trying to say. So basically the receiver knows that this is a valid code word. Now these are known, so you can say these are known to both sender and receiver. These are known to both sender and receiver, right? Now suppose that these are the number of valid code words 1100. Okay, then total number of ones, let's suppose, should be even. So let me add 0 1011, and then let me add 1 1101. Let me add 1 here. Okay, suppose these are set of valid code words. These are set of valid code words which are known to both sender and receiver both, right? Now suppose you are transmitting 11000. Suppose you are transmitting this. Now I mean, basically my idea is that you are transmitting some valid code word, right? And then here also you are receiving, I mean, receiver is also receiving the valid code word. The valid code word need not to be the exact same, it could be something different. For example, 11011. Okay, this is also a valid code word. I mean, number of ones are even. Okay, here also number of ones are even. So if you are sending valid code word and receiving also valid code word, then in that case receiver will not be able to detect the error. Okay, so receiver will not be able to detect the error, because receiver is thinking it is valid code word. It doesn't know that it is got corrupted and then got valid, right? It receiver will think that originally it might have sent something like this. Okay, so receiver will not be able to detect error. So what I'm trying to say, that if you are sending a valid code word and receiving also valid code word, then receiver will not be able to detect the error. But if you are sending a valid, obviously you will always be sending the valid, right? I mean, why will you send invalid? So if you are sending some valid code word, but at the receiver time you get some invalid code word, then only, okay, in this case only receiver will able to detect the error. This is a general method, okay, general thing. Receiver will be able to detect error. Understood? So if you are sending valid but you receive invalid, then in that case receiver will be able to detect the error. But if you are sending valid, receive also valid, then receiver will not be able to detect the error. Okay, so that's what the valid and invalid means, right? So valid code words are known to both sender and receiver, which means, I mean, these are the valid code words. These are known to both sender and receiver. Also knows that, okay, total number of ones should be the even. Okay. Anyway, so they are saying, let's suppose these are the valid code words, right? I mean, this the sender will be sending, but after some bit get flipped, okay, this might get converted to this, or this might get converted to this, or this might also get converted to some other valid, which is I mean, receiver will not be able to detect, which is fine. Okay. Anyway, the question here is different. They are saying that find out the minimum Hamming distance between set of valid code words. See, here the distance is 1. Here the distance, I mean, total distance from here to here is 2, and then so basically the total distance between the valid code words, obviously this is 3, right? I mean, if these are the 2 invalid in between, then 3 is the distance. 1 2 3, right? 3 distance here, but only 2 distance here. So what is the minimum distance? Minimum distance is 2, right? So what is the answer? So D minimum, or the minimum Hamming distance, is basically 2 because of this, right? Although there are the 3 distances there between these two, okay, but still the minimum is 2. I hope you understood. Okay, that's how you find out the minimum Hamming distance. Now let's just see this. So they are saying that find out the minimum Hamming distance again. Okay, I mean, this is the valid one, these are the valid ones, and then they are saying that these are the invalid ones. Okay, see, between these two valids, minimum, see, this 3 invalid is coming, then which means the distance is 4 basically. 1 2 3 and 4. Okay, between these two valids the distance is 4. Between these two valids the distance is again 4. But between these two valids the distance is 3 only. So that's why the minimum is 3. Okay, minimum is 3. I hope you understood. Minimum is 3. Why? Between these two valids. Okay, 1 2 and 3. Minimum is 3 distance. Although 4 distance also present, but minimum is 3. Okay, great. Consider the group of valid code words shown in the what is the receive? Yeah, this is interesting. Now you know that how to find out the distance, minimum Hamming distance. Now let's just see, will the receiver be able to detect the error? Okay, based on this Hamming distance and all. So suppose that this is a scenario, which means you have some valid code words, and in between there is some invalid also, which means that this is valid, but between two valids, okay, the distance is 3. Okay, the minimum having distance is currently 3. They are saying if there is I mean, this could be 1011, and this could be again let's suppose if you change the 3 bits, then it could be 0101. Okay, something like this. Okay, so basically the distance between these two is basically 3, right? 1, 2, and 3. So these are the valid code words, suppose. Okay, so I mean there could be more bits, doesn't matter. So yeah, these are the valid, this is the valid code word, suppose. Okay, let me have 001, just to 001. Okay, suppose these are the two valid code words, and then this is again valid, this is again valid. I'm not interested in these numbers. Okay, I'm not interested in these numbers, that's why I'm not writing these numbers. The question is that will the receiver be able to detect 1-bit error? Suppose 1-bit error occurs, okay, which means, let me go to the next page. What does this mean? Just understand this, and then you will understand the whole topic. Suppose 1-bit error occurs, which means this valid code word will get flipped to this. Okay, I mean, it will not go here, it will not go here. See, this is important. This will get flipped to this, or this will get flipped to this, or something like this, right? I mean, if you are having 1-bit error, then the whatever you are sending, you will not be receiving this. I mean, if you are sending valid, you cannot receive the valid. Okay, if you are sending valid, okay, which means if after 1 bit of the flip, you will be always getting invalid. See here, if you are sending this, then after 1 bit of the flip, okay, any of this, okay, after one bit of the flip, you will always be getting the invalid. So receiver will be able to detect the error, right? If this is the situation, which means if the minimum having distance between any of the two is 3, okay, then 1-bit error will be detected. Which means if you are sending any valid, then you cannot get the valid after 1-bit error, because between two valids there are 3. You have to flip 3 bits. Okay, even you can detect 2 bits, not just 1 bit. You can detect 2 bit of error, because after 2 bit also you are getting invalid. But can you detect 3 bits of error? No, because you are sending this, and you might be at the receiving end, you might be receiving this. So your receiver will not be able to tell whether the error has been occurred or not. Okay, so basically in this case, if you ask me, if given this situation, okay, given this situation, don't worry about this. Given this situation, you ask me that can receiver detect 1 bit of error? Then yes. Can receiver detect 2 bit of error? Yes, because after 2 bits also you are getting invalid. Can receiver detect 3 bits of error? Then answer is no. Okay, so if I ask you, can in this setup, okay, receiver detect 1-bit error? If 1-bit error occur, then can receiver detect it? Then answer is definitely yes, right? Okay, then answer is yes. Now if I ask you the next question, which is, can receiver detect 2 bit of error? Then the answer is definitely no. Then the answer is yes. But if I ask you, can receiver detect 3 bit of error? Then the answer is definitely no, right? If I ask you 3 bit of error, can receiver detect 3 bit of error? Then the answer is no. Okay, it can error detect 1 bit, because after 1 bit flip you will be getting invalid, then invalid. Okay, after 3 bits of flip you will be getting valid. So receiver will not be able to detect 3 bit of error. Okay, now let's understand more example. Now in this situation, tell me, will the receiver will be able to detect 1 bit of error? In this situation, tell me. See here, after 1 bit flip only you are getting the valid again. So that's why the answer is no. So here the answer is no. Why? Because you might be sending this, and after 1 bit flip you are getting this. So receiver will not be able to know. Receiver will think this is a valid code word. So how would receiver know that there is an error or not? You're getting my point? So the thing here is that if you are getting the valid again, then receiver will not be able to detect. So yeah, if I ask the same question, and if I remove this, okay, suppose this is not there. I mean the minimum having distance, I mean the code words are like this. If you flip 1 bit, you will not be getting the valid. Okay, you will be getting invalid only. Then in this case the answer is yes. Because after flipping 1 bit you are getting invalid. So yes, receiver will be always be getting invalid after 1 bit of error. So yes, receiver can detect. Okay, let's solve more question. how many bits of the error receiver can detect given this situation? Given this situation, which means this is valid, but in between there are few invalid. If 3 invalid, which means the 4 is the Hamming distance. So how many bits of the error? See, 1 bit is okay, 2 bit is okay, 3 bit is okay, but the moment the 4 bit of error occur, then the receiver will not be able to detect the error. Okay. So here everything is same. I mean, I'm taking the minimum one. I have to take the minimum distance. So currently everything is same. So I'm taking just random. So you can I can modify the question. Okay. So I will modify the question just a minute. But before that, let me solve this question. So how many bits of the error you can detect? 3 bits. Why? Because 1 bit error you can detect, 2 bit error you can detect, 3 bit, up to 3 bits is fine. Okay, this is fine, this is fine, this is fine. But the moment this is 4th bit, okay, the moment you get 4 bit of error, the moment you get 4 bit of errors, then in that case it will be again valid. So receiver will not be able to detect this error. So up to 3 bits you can detect. Or in other words, if there are like distances 4 between the minimum Hamming distance between two valid code words is 4, which means there are 3 invalids in between. If the distance is 4, which means there are 3 invalids in between, which means up to 3 invalids you can survive. So up to 3 bits you can survive. But the moment you are having 4 invalids, then you will not survive. Okay, or the 4 bits flip, you will not survive. Okay. Now let me ask the same question. How many bits of the error you can detect here? But let me modify the question. Let me say this. Okay, let me ask the same question, but let me little bit modify this. Okay, then what is your answer? See, you always go for the minimum Hamming distance. See, currently this is 4 distance, this is 4 distance. Let's not worry about it. The here let's just check. See, 1 bit error is fine, 2 bit error is fine, but 3 bits of error you cannot detect. So up to 2 bits error you can detect. So you can say up to 2 bits of error. Okay, see here also you can obviously use up to word, up to 3 bits of error. I hope you are getting that how to find out, right? So if the minimum Hamming distance is 3, 1, 2, 3, then up to 2 bits of error you can detect. Why? Because the number of invalids, if the minimum Hamming distance is 3, the number of invalids in between is 2. So you can land up in the invalid, which means if you are landing up in this invalid or in this invalid, then you can detect, right? So you can say, that if D minimum is, let's suppose, S, minimum Hamming, D minimum means minimum Hamming distance. Minimum Hamming distance is, let's suppose this is S, then we can detect D minimum minus 1 bits of error, right? Bits of error, which means if the minimum Hamming distance is 3, then you can always draw the diagram. You don't have to remember these things. Okay, minimum Hamming distance is 3, which means what? These are the 2 invalid in between. Let's suppose this is valid. Okay, this is full, this is valid. Then minimum Hamming distance 3 means this is 1, 2, 3. Yeah, minimum Hamming distance 3 means 2 invalid in between. Then how many bits of error you can detect? 1 and 2. That's all. You can always draw this diagram and you can always find out the answer. Yeah, or it's this very simple formula, minus 1. If you want, you can remember this. Otherwise, you can draw that. Okay, minimum Hamming distance is 3, then which means 2 invalid in between, which means up to this, if you land up to this, or if you see from here, if you land up to this, then you can detect the error. Otherwise, you will not be able to detect the error. Okay. So how many bits of error you can detect? This is a question. Okay, in this question, they are also asking that how many bits of error you can correct. This is interesting. Okay, so detect and correct, both they are asking. So how to correct, let me just tell you, and before that let me first answer the question that how many bits of error you can detect. So how many bits of error you can detect? Since there are 3 invalid in between, in a minimum 3 invalid in between, so 3 is the answer here. Very straightforward. Or in other words, this is like 4 distance, 4 minimum Hamming distance. So 4 minus 1, 3 is the answer. So you can, if you land up in this, if you land up in this, if you land up in this, then you can say that okay, 3 bits of error you can detect. But how many you can correct? This is the next question that we want to answer. Okay, how many bits of the error you can correct? Very interesting. See, when can you correct? Let me just tell you when can you correct, and then you can answer this question. See, this is the setup. Okay, I'm not very much interested in the numbers because numbers will only confuse you. It could be any number, this could be some other number. I mean, okay, numbers will confuse you. I'm not very much interested in the number. Let's just see how you can correct. See, you can correct only when you are basically sure that for this valid, okay, for this valid, okay, let's suppose if there is only one bit of flip, then you will be getting this invalid only. For this valid, this invalid only, or this invalid, right? I mean, so basically what I'm trying to say, that for this valid you can get only these two invalid. If this is only one bit of error, right? If this is only one bit of error, then you can get for this valid this is the only invalid, for this valid these are the two only invalid, for this valid these are the two only invalid, for this valid this is the only invalid, right? Something like this. Okay, if this is one bit of error, then the invalids are not overlapping, which means you can correct one bit of error. Wow, how? Because whatever you get, if I'm sure, okay, if I'm telling you that at most one bit of error can occur, okay, then the moment you get invalid, let's suppose you transmit some valid, okay, some valid you transmit, okay, and then you get at the end, let's suppose you get invalid, then you know there is an error, but can you correct that error? That is the question. Okay, that is the question. See, you are getting this invalid, can you correct it? And then can you fix it? You can correct it only when you know that from which valid it got flipped. But since you know that for this, I mean, the combination is fixed that for this invalid, okay, for this invalid, the only possible valid is this, because the invalids are not overlapping. What do I mean by that? See, if we have our own set of invalids, then we can even correct the error, which means, let's suppose I say here, let's suppose I say that you can have 3 bits of error. Can you correct 3 bits of error? The answer is no. Up to 3 bits of error can you correct? Answer is no. How? Why I'm saying so? Because if you have 3 bits of flip, up to 3 bits of flip, then you may be flipping this from here to here, or you may be flipping this, if this is just 1 bit of error, from here to here. So once you receive this invalid, you do not know that what was the original valid, right? Once you receive this invalid, you do not know what was the original valid. So basically if up to 3 bits of error occur, then we can detect it, that because we are ultimately in getting the invalid, we can detect it, right? I mean, we will be getting invalid, so we can, up to 4 bits of error we cannot detect it, but then we can detect it. Obviously we can detect the error, but can we correct it? Answer is no, because for this invalid, we do not know from where it has come. I mean, what was the original valid? Maybe this is the original valid, or maybe this is the original valid, right? So there are two possibilities, or even there could be multiple possibilities there here also. Like in 2D, if you see, I mean, basically for this there could be many different possibilities that from where this invalid is coming, right? So so currently what I'm trying to say here is that if you are getting this, then you do not know what was the original valid. But suppose, okay, you know what was the original valid, then which means if the set of invalids are separate, okay, which means if I get wrong, then at most I can get wrong till here. If I get wrong, then at most I can get wrong till here, right? If the set of invalids are not overlapping, then I can even correct the error, okay? So if set of invalids are not overlapping, then we can even correct the error. Set of invalids are not overlapping, then we can even correct the error, okay, which means I know that, okay, for this is the only set of invalid, 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 then I can correct. I know if this is the invalid, then I know that this must be from this, okay? So in this case I can correct up to 1 bit of error, okay, because the moment you have 2 bit of error, then these will not be non-overlapping, right? So which means the moment you have 2 bit of error, then the problem is that number of invalids will not be non-overlapping. I mean, they will be overlapping, right? So 2 bit of error you cannot detect, okay? So if you're having overlapping invalid, so basically this is overlapping, so 2 bit of errors you cannot correct. Detect, you can detect 3 bits of error, 2 bit of error we cannot correct. Okay, so one bit of error we can correct, because in one bit we know that, okay, what if this is invalid I'm receiving, I know that what is the corresponding valid, right? If this is invalid, I know what is the corresponding valid. But if two bits of error is occurring, then if this is invalid, then I do not know whether this is come from this or this is coming from this. Okay, I do not know, right? So that's why I cannot correct it. That's the idea. Now you will get to understand more with the more examples, right? So suppose if I ask you, just a second, yeah. So suppose if I ask you here that the minimum having distance is d, then how many bits of error you could detect? I'm just asking detect. So I think answer is, you already know, d minus 1, right? D minus 1. Answer is already, you know, d minus 1. So d minus 1 is the answer. But if I ask you in the same question, how many you correct? Okay, how many you can correct? Maybe I might be having, yeah. Let's suppose, yeah, let's solve this question. Will you be able to correct one bit of the error? See, for one bit, obviously there is no problem. I mean, the set of invalids are completely separate, right? Yes, I can correct one bit of error. So the answer is yes. So you can say, since this is non-overlapping, so the answer is yes. Will the receiver be able to correct one bit of error? Answer is yes. In the same question, if I ask, or maybe I don't know if I, yeah, the little bit change question, will the receiver be able to correct one bit of error? See, earlier the distance, these are the three invalids in between, but I think now there are two invalids in between. Okay, now tell me, will the receiver be able to correct one bit of error? Detect, for the detect, I just need to count the Hamming distance is 3, so you can even detect 2 bits of error. Okay, I mean, even you can detect 2 bits of error, right? Will be able to correct 1 bit of error? I'm just asking this. For the 1 bit, you just need to check. Okay, for the correction, you just need to check this should be non-overlapping. Okay, is this non-overlapping? That's all you need to check. Okay, this is obviously okay, this is okay. I think this is again non-overlapping, right? Since this is non-overlapping, you can say yes. Yes, set of invalids must be non-overlapping. Okay, so will you be able to correct one bit of error? Yes. Here also you will be able to correct, even though the distance is actually 3. Here also the distance is 4. Obviously, the more distance is better. But even the distance is 3, then also you can correct. Okay, in this case, for example, this case. But let's suppose the distance is 2. Then will you be able to correct the 1 bit of error? Okay, let's suppose I ask the same question. Okay, but here the distance is, let's suppose, 2, which means, let me little bit modify this. I need to have minimum having distance 2. Okay, so you can modify this also, but if you have modified 1, that's fine. Okay, so will you be able to detect 1 bit of error? The answer is no. Why? Because here this is overlapping. Here this is overlapping. Will we be able to detect one bit of error in this case? Then answer is no. Okay, here it is overlapping. So basically, you can answer these questions. Will you be able to correct? Okay, sorry, if I'm saying detect, actually it is correct. So if you will you be able to correct, then answer is no, because this is overlapping. Okay, since it is overlapping, that's why if this invalid is coming to the receiver doesn't know if after 1 bit of flip one bit of flip is from here or 1 bit of flip is from here, then you cannot correct it. Okay, you can detect it. Yes, you can detect it. Detect, yes. Why? Because minimum having distance is 2, so 2 minus 1 is 1, so you can detect 1 bit of error. Which means if this is coming, you know there is an error. Then, but you do not know what was the original one, right? Okay, so basically the set of you can say the invalids should be non-overlapping, something like this, right? So how many bits of error you can correct here? See, I think you can divide into half, basically, right? You can divide into half. This is, yeah, I think 2 bits, right? I think 2 bits, because if you take 3 bits, then it will be overlapping, right? So you can divide into half. If it is odd, then okay, you cannot make much use of this. So you can say up to 2 bits of error you can correct. So which means something like this. Let me just do that. Okay, up to 2 bits of error you can correct, because up to 2 bits there is no problem. Okay, so how many bits of error? 2 bits of error you can correct. I hope you are getting the point. So how to decide, I mean in general, how to take a call? So basically what we are doing, we want the non overlapping invalids, right? So what we will do, we will have the minimum having distance. Let's suppose this is where the minimum having distance is occurring. So basically I mean currently I'm taking everything even, which is fine. Okay, I mean here whatever distance I'm taking is continuous here, but we will basically work on the minimum. Okay, so basically what we will do, we will divide the minimum having distance into two parts. Okay, into two parts, and then one part I will give to this, one part I will give to this, which means I will say if this distance is d, right? If this is the minimum having distance, the number of invalids will be d minus 1. I mean number of invalids in between is basically d minus 1, and I'm dividing number of invalids equal parts, okay, by 2. So these many bits of error you can say, if minimum having distance is d, then these many bits of error you can correct. Okay, so these many bits of error you can correct. So currently the minimum having distance, this is 3, 5. So it is 6, right? So 6 minus 1 divided by 2, which is 5 by 2, which is 2.5, which is 2, right? I mean, you obviously need to take a floor, okay? Because you cannot go for more, okay? So you need to take the floor. So basically, I mean, integer part you need to take, right? So basically 2 is the answer. Okay, so you can correct up to 2 bits of error. How many bits of error you can correct? 2 bits of error. Because whatever is the minimum having distance, you need to divide that into 2. Minus 1 plus 1 we can adjust, but yeah, we need to divide into 2, and then we need to say that, okay, this is your set of invalids, this is my set of invalids. Okay, if I'm separating the set of invalids, then I can correct also. Okay, so suppose if the minimum having distance is 15 here, then how many bits of error I can correct? I need to divide this in 2. Okay, so I can say 7 distance I can 7 basically bits of error I can correct. Okay, so what is the answer here? 7. Understood? If this is 8, the minimum having distance is 8, then it is actually not 4, because number of invalids are basically 7 in between. So 3 you need to give to 1, 3 you need to give to 1, 1 will anyway be remaining. So 3 is the answer. Or in other words, you can use the formula d minimum minus 1 divided by 2, which is basically 8 minus 1 divided by 2, which is 3. Okay, I mean 7 by 2, which is 3.5, but you need to take integer. 3 is the answer. So how many bits you can correct? For that you need to have separate, which means by 2 will come. Okay, by 2 will come. By 2 means number of invalids you need to separate. So number of invalids you need to divide number of invalids into equal parts, which means number of invalids will be distance minus 1, and you need to divide that into equal parts. Something like that. Otherwise you can make a diagram, and at that time you can basically for the small number you can check that what to do. Okay, then you can answer for the 8 or 15 or whatever. Okay, for 2, 3 I mean minimum having distance is 3. For that you can make a diagram. Okay, this is minimum having distance 3, which means you can detect only 1 bit of error. You can correct only 1 bit of error, not detect you can detect 2 bit of error, but you can correct only 1 bit of error if the minimum having distance is 3. Okay, I mean you can make the diagram, and then you can separate the set of invalids. This is very interesting idea, isn't it? Now to guarantee S that correction up to the S errors, which means I can correct S errors. This is the reverse question actually, which means I need to have how many what should be the having distance. If I need to make sure that, okay, I can correct S bits, which means there should be S invalids separately here, S invalids separately here. Okay, which means 2S invalids in between, 2S invalids in between, which means having distance will be 2S plus 1. So C is the correct answer. Okay, if 2S invalids in between, the having distance will be 1 more than that. Okay, so 2S plus 1 is the answer. Understood? So I hope you are getting my point, that how to correct. Basically to correct you need to have separate set of invalids. That's the key point. Okay, so the key point is that to correct error, we need to have separate set of invalids. Okay, and then you can correct. Okay, and to detect the error, we just need to make sure that we are not passing to the valid, which means that if you want to detect some error, okay, then we just need to make sure that we can detect 1 2 3 4 5 up to 5. Okay, we are not going here. Okay, that's all. But to correct the errors, you need to make sure that separate set of invalids should be there. Okay, separate set of invalids. Okay, now let's solve this question. So basically, to guarantee up to 5 bits of error, that you can correct up to 5 bit of error. So basically, for s, 2s plus 1 is the answer. So it is a general formula that if you want, okay, that s bit of error should be corrected, then the answer is 2s plus 1. So here the answer is 10 plus 1, which is 11. Okay, so 11 is the correct answer. Understood? So basically, to correct up to d bits of error, I need 2d plus 1 distance. Okay, let me write it here. To correct up to d bits of error, I need 2d plus 1 distance. Okay, basically it is Hamming distance. So which means, I mean, at least I need, which means obviously Hamming distance could be greater than 2d or 2s, whatever you like to say. I mean, it could be greater than that, but yes, at least it should be at least 2d plus 1. And to detect, let's suppose I ask the same question, but to detect up to d bits of error, how many what should be the distance if I want to detect d bits of error? Okay, which means, let's suppose this is, if I want to detect 4 bits of error, then 4 invalids must be there in between, right? So the Hamming distance, minimum Hamming distance should be what? See, if I want to detect, the 4 bits of error, right? So 4 invalids, so minimum Hamming distance should be d plus 1, isn't it? So to detect up to d bits of error, the minimum Hamming distance should be d minimum must be d plus 1, greater than or equal to d plus 1. Understood? But if you want to correct d bits of error, then it should be okay, if you want to correct up to d bits of error, then I need basically 2d invalids in between, right? In that case, I need 2d invalids in between, which means the distance should be 2d plus 1. But if you want to detect only, then I need d invalids in between, which means I need d plus 1. Okay, I need d plus 1. I hope that is fine to everyone. So that is the only thing that I wanted to convey here. So these two formulas, most of the aspirant actually by heart, and then they think that okay, this is the formula to be by hearted. But actually, you can understand and that why that is the case. Okay, so with these diagrams, I hope it help you a lot to understand these two cases. And I might have, yeah. So already in the slides also. So I've taken this from this university. This is from Frozen, and this paragraph is from this university. So 2d plus 1 for the correction, okay, 2d plus 1 for the correction, d bits of error, and for the detection, okay, d plus 1 or s plus 1. Okay, so yeah, these are the numbers. So actually sometimes they flip also. I mean, they will give you for example, they can ask you the question. Let's suppose that up to d bits of error you want to correct or detect, whatever they will ask, and then what is the minimum Hamming distance is needed. Minimum Hamming distance needed. Okay, required or needed. So this is one way of asking, which means they will say that okay, up to d bits of error for the correction. Okay, you will say minimum Hamming distance is needed is 2d plus 1. Okay, for the detection, they will say, you will say d plus 1. Okay, this is one way of asking. In another way also, they ask the similar type of question. They just flip the direction. Okay, instead of this, they say something like this. So basically, they will say the minimum Hamming distance is d. Okay, they will give you the minimum having distance, could be anything, let's suppose D. Okay, then how many bits of the error how many bits of the error you can correct or detect. Okay, so they will say that minimum having distance is, they will give you some number is D, let's suppose D. Then they will ask you how many bits of error you can firstly detect and then correct. Okay, something like this. You can detect and second correct. So if the minimum having distance is D, which means D minus 1 is basically number of invalids in between, right? D minus 1 number of invalids in between. It means that you can detect up to D minus 1 bits of error. D minus 1 bits of error you can detect. And how many bits of error you can correct? So among these D minus 1, you need to basically divide into half, right? D minus 1 by 2. D minus 1 by 2, you get integer part. Okay, for the integer part, you can take like this. Okay, these many you can correct. Okay, so these many you can correct. So basically they can ask you the question in this way also, that up to D bits of error, we want to correct up to D bits of error, what is the minimum having distance required. They can ask the minimum having distance, or they can give you the minimum having distance and then can ask, okay, how many bits of error you can detect, how many bits of error you can correct. Okay, given this. Or they can ask in the other way also. So they can ask in any way. Don't get too much confused. You just make this diagram and this and then have your concept in place. You can answer all the questions. Okay. So these are the two ways of asking question. Okay. So let me write two ways of asking questions. Right. So sometimes they ask number of or the minimum having distance needed. Let me write D minimum needed to correct or detect D bits of error. Or sometimes they ask that minimum, sometimes they ask like this. They ask how many bits of error you can detect or correct. Okay, how many bits of error you can detect or correct given minimum having distance, right? D minimum. Given this, how many bits of error you can detect or correct. Sometimes they ask like this. So there are two ways of asking. Don't worry about the ways. Okay, you can just make the diagram, just divide into half for the correction, or for the detection you can just take a call. Okay, so that's how you can solve these type of questions. Okay, now let's solve few questions. For example, this question has been asked in GATE 2007. So they are saying that these are the these are the code words. What is the maximum number of bits can be corrected? Okay, first of all, find out the minimum having distance. So if you find out the minimum having distance, this is 10101, I think. Yeah, I think the minimum having distance you can find out. So basically it is coming out to be 5. Okay, it is coming out to 5. Now how many bits you can correct? So basically if they are asking how many bits you can correct, then 5 minus 1 by 2, right? 5 minus 1 by 2 is the answer, which means 2. Just a second. For the detection, is it coming out to be 4 or 5? Okay, these are the 4 bits only. Okay, I thought these are the 5 bits. Sorry, these are the 4 bits only. So minimum having distance is coming out to be actually 4. Okay, then how many bits of error you can correct? How many bits of error you can correct? 4 minus 1 divided by 2, right? Which means 3 by 2, which means 1. Okay, integer part you need to take. So 1 bit error you can correct. Okay, let's solve the next question. For the detection of 5 bit of error, okay, the minimum having distance in the block must be, if you want to detect 5 bit of error, which means 5 invalid must be there in the between, it means 6 should be the answer, D plus 1. Okay, so 6 is the answer here. Understood? Let's solve more questions. So let's solve this question. This question is asking UGC net. So they're asking, consider a code with the 4 valid code words. Okay. So yeah, here the minimum having distance, if you find out, this will be 5. Okay, this is 5. Now they are saying the code, okay, they have given that code has the distance 5. Distance 5 means minimum having distance is 5. If the code word arrive is something like this, something corrupted has arrived, okay, then the original code word must be. See, with this minimum having distance, we can correct up to 2 bits of error, right? We can correct up to 2 bits of error. Now they're asking that the code word arrive is this. So basically it must be, you can correct up to only 2 bits of error. See, this question is little bit not well framed, I can say. So they cannot say just like this. I mean, they must say that, okay, at most 2 bits of error. So they are saying that we are, see, let me just first tell you the question. They are saying that we are getting this, right? Which is invalid. Now they are saying that what could have been the corresponding valid? I mean, the original code word must be. That's what they are asking, right? See, the original code word could be anything. I mean, the question is not well framed, I would say, because this is UGC net question. The original code word could be anything, right? It could be anything. You can get this from this, right? You can get this from this. You can get this from from this. You never know that how many bits of error has been occurred. So they should give in the question itself. The question is little incomplete. They should give that some channel property. Okay, they should say some channel property. Let's suppose if I give you some channel property, and if I say that in this channel, okay, in this channel, up to 2 bits of error can happen. Okay, suppose they say something like this. I mean, some channel property. I mean, something like this, right? Then you know that, okay, up to 2 bits of error, after 2 bits of error only you should be getting this. So it must be basically, you can make these two as ones. Okay, it must be only the one corresponding valid will be there, which means something like this. Okay, A is the answer. A is the answer. I mean, making 2 bits flip, you can get only A. You cannot get anything else. Okay, you cannot get B, you cannot get C, you cannot get D, something like this, right? I mean, after 2 bits of flip, you can get only A. See, if there is any number of flips are allowed, then you do not know the original code word, right? So they should give, I mean, in this question, they should give that, okay, up to 2 bits of error can happen. Because we can also correct up to 2 bits of error, that's fine. Okay, that's fine. But originally, how many bits of error has been happened, we do not know. So they should give in this question. Okay, we can correct up to 2 bits of error. This is I agree. Okay. But there may be multiple errors also. But if the channel is saying, okay, up to 2 bits of error can happen, then yes, we can even correct them. Okay, and then A is the correct answer. Okay, little bit ill-framed question, I would say. Let's solve this question. In this question has been asked in GATE 2017. They are saying that 4 valid code words are given. Let the minimum distance between the code is P. Okay. So by the way, you can quickly find out the minimum having distance. This is coming out to be 4, but there could be 1, 0, 1. Okay, so 3 bits are flipped here from this and this. I think this should be 3, right? I mean 3 or 4. If I need to choose between 3 or 4, then 3 is the correct one. So minimum having distance, D minimum, is basically 3, right? Is 3. Is P and this is 3. And the maximum number of erroneous bits that can be corrected. Okay, so how many bits you can correct? 3 minus 1 by 2, which is 1, right? You can correct up to 1 bit of error. So A is the correct answer here. Okay, A is the correct answer. That's easy question. So you need to find out the minimum having distance and how many bits of error you can correct. Depending on the minimum having distance, you can calculate it. Okay. Now, now let's see one interesting, and I can say it is at the same time bit optional. I can mark it optional. Okay, one interesting thing, which is that how to develop such error correcting codes. Okay, which means that how to make sure that my code is always having, let's suppose I need single bit error correcting. Okay, which means if I need single bit error correcting, minimum having distance must be 3. So how to make sure that my minimum having distance is always 3? Okay, how to develop such codes. So suppose we want to correct single bit errors, hence you must be having minimum having distance 3, right? Hence the next question is how to develop such codes. This is my question. Okay, so this is the next topic, which means we have covered most of the things. So, and you can say this slide is basically the most important slide, which is the summary. Okay, this slide is most important slide, which is the summary. I mean, D plus 1 and 2D plus 1 and D plus 1 are the correct answers. Okay, this slide is summary. This is the most important slide. And then now we are seeing that, okay, that's fine. Like, okay, we need three distance to correct 1 bit error, or we need 5 distance to correct 2 bit error or something like this, right? So basically we have gotten the idea that, okay, what is the need, but how to develop such codes? Let's just see how to develop such codes, right? So hence the next question is how to develop such codes. So suppose we have 4-bit data. We will be adding parity bits to make it in such a way that any invalid code word is at least 3 bits away. So suppose this is the 4-bit data. I want to make sure that I want to add some parity bits, and I want to make sure that any two valid are at least 3 distance away. Okay. So basically the idea is that I need to add some parity bits. So how to develop such codes? See, originally you have the data, right? Then we will be adding the parity bits. Okay, so here we are adding the three bits. In order to achieve this, we will be adding parity bits to the data. So such that I will somehow, I will tell you that how, but I will somehow make sure that any two valid code words are at least 3 bits away. How? Let me just tell you. We will add in such a way that even if one data bit changes, okay, let's suppose you are changing this, okay, you have to change 2 parity bits, then automatically 2 parity bits, some of the two parity bits has to be changed, hence total 3 bits has to be changed. Okay, basically any two valid will be 3 bits away. I will tell you how. See, suppose this is the original data, and suppose if I'm adding these parity bits, right? So something like this, P1, P2, P3, in such a way that P1 is calculated like this, D1, JOR D3, JOR D4, okay? P2 is calculated like this, P3 is calculated like this. Then in that case, even if you change 1 bit, okay, let's suppose you're changing D1, okay? If we change D1 here, then what are the bits that automatically get changed? Change D1, then P1, P2 will automatically get changed, because P1, P2 is basically having D1. Okay, I'm just changing D1, then P1, P2 will automatically get changed. Automatically, okay, get changed, isn't it? Similarly, if you change D2, then P2, P3 will automatically get changed. If you change D4, then P1, P3 will automatically get changed. If you change D3, in that case, all of this will automatically get changed. The distance will be 4, which is fine. I mean, D3 will be changed, and then D3 will be changed. So total distance will be 4, but the minimum will be always 3. Okay, even if you change any of the bit, okay, even if you change any of the data bit, then automatically more than 1, okay, the parity bit has to change, which means the 3 distance is automatically maintained. Let me just tell you example. Okay, then how to correct? See, first let me first tell you some example. Probably then you will get to understand. Suppose this is the data. Okay, then let's first calculate this P1, P2, P3, okay, using this formula. Okay, P1, P2, P3 basically is computed like this. So you can calculate it, right? So let me just tell you the answer if I have here in the slide. Okay, in the slide I do not have the answer, so let's just quickly calculate it. D1, D3, D4. So D1, D3 and D4. If you JOR this, then you will be getting 0. So P1 will be 0. What about P2? P2 is D1, D2, D3. If you JOR this, you will be getting again 0. Right, D2, D3, D4, you will be again getting 0, right? Okay, so these 3 bits are 0. So what will the transmitted code word? 1, 1, 0, 1, and then 0, 0, 0. Okay, this will be your transmitted code word. Now let's suppose one of the bits get flipped. Let's suppose this was D1, D2, D3, D4. One of the bits get flipped. Let's suppose D2 get flipped. Okay, you are transmitting this and D2 get flipped. Will you be able to detect or correct this 1 bit of error? Let me just check. Okay, this D2 got flipped. Then you will anyway calculate P1, P2, P3, right? If you calculate P1 at the receiver side, then it will D1, D3, D1, D3, D4, D1, D3, D4. So P1 will be correct. Okay, P1 will say that, okay, there is no problem. But what about P2? P2 will say D1, D2, D3, D1, D2, D3. P2 will say the answer should be 1, but you are writing 0 here. Okay. P2 will say something is problem. I mean, P2 will not be able to exactly tell that what is the problem, but P2 will say some problem. I mean, it will detect. Currently, I'm not correcting. I mean, by looking at only P2, I cannot correct. It will say something wrong, right? Now, you will check P3. P3 is saying D2, D3, D4. Okay. If you check D2, D3, D4, it is again coming out to you 1. So, P3 will again say something wrong, but it is 0, so something wrong. Okay. So, just check if these two are wrong, which means what is common between these two? D2 is common, which means D2 must be wrong. Okay, that's how we can correct also. Okay, so that's how we are basically developing the codes which can even correct the codes. And we are always making sure whatever you do, if you are calculating in this way parity bits, whatever you do, minimum having distance will always, the moment you change one data bit, automatically 2 parity bit will be changed. So always the minimum having distance will be 3. Okay. Okay. So basically we are developing codes in such a way that automatically the minimum having distance is 3, right? But currently it was a 4 data bits only, okay, 4 message bits only. But can we extend this idea to n message bits? Suppose there are n message bits, okay, D1, D2, D3 till Dn. Then can we extend this idea to n message bits? Which means can we make sure that that minimum having distance must be 3 even if there are 100 bits? So obviously the two natural question arises that how many parity bits should I need? Okay, so the two questions, how many parity bits are required and how to calculate those parity bits. These are the two questions which I need to answer if I want to extend to the n bits. So again, this is extremely optional. Okay, this is very much optional. I just want to, I will just go through this, okay, very quickly. So basically the idea here is that we want to extend to the n bits. If we want to extend to the n bits, then I first need to make sure that how many parity bits are required here. Okay, number of parity bits, how many parity bits I require to make sure that, okay, everything is working fine, and how to calculate those parity bits, right? So let's answer this question. Let's answer the first question, that how many parity bits are required. So since this is very optional, so I will keep this in the next video, and I will make that video optional video. Okay. So, but if you ask me like what is the key takeaway of this lecture, then I can say that this is the key takeaway, that if the minimum having distance is D, in that case, okay, you can divide by 2, then number of invalids will be D minus 1. So correct up to D minus 1 by 2 and deduct up to D minus 1. Or in summary, you can write like this, that up to D bits of error correction, then minimum having distance needs is 2D plus 1. If you want up to D bits of error deduction, then minimum having distance needs is D plus 1. If minimum having distance is given, which is let's suppose D, then you can deduct up to D minus 1. Bits of error. Minimum having distance is D, which is given, then you can correct up to D minus 1 by 2. Okay, the integer part you need to take. Okay, so this is the key summary for this lecture. I hope now you, instead of remembering the formula, now you can visualize, you can make the diagram, and then you can solve these kind of questions. Okay, because they can trick you anywhere. Okay, so that is all for this lecture. Thank you, everyone.